Welcome. For the time being, we are finally reaching our last video tutorial on purely geometric techniques for a little while. And the techniques we're going to develop in this tutorial have to do with accurately dividing a given segment into not just 2, 4, 8, 16, 32, or so on equal pieces, but any given number of pieces. So if I want to divide a segment into 7 pieces, I ought to be able to do that. Once we've got that skill in place, we'll immediately turn it around and use it together with our new knowledge about parallels and right angles, and we'll use it to start laying out rectangles and squares, and in particular rectangles whose sides lengths exist in whole number rational relationships to each other. Just like we saw with our very first design workshop of the stool, where there's a bounding box around the front elevation view of the stool, where the width was in a 3:2 ratio with the height. So anyway, suppose we have this problem of dividing a segment into a chosen number of equal pieces. I'm going to demonstrate this technique by example, and I'm going to do it for a specific number of pieces. I'm going to divide a given segment into 5 pieces. They're all going to be equal. So here's the setup. Here's our segment. AB, if you want to give it a name. And off of AB, from the point A, I am going to draw a line that goes off for some distance, comparable to the length of AB, or maybe a little bit bigger. Any of those ought to be fine. Now what I'm going to do is I'm going to eyeball that segment, and I'm going to try to set my compass to a smaller size that I ought to be able to fit 5 steps of this size onto this new line. So I'm going to start at A, mark off once, twice, 3 times, 4 times, and a 5th time. And then from A to that last mark, I'm going to label those as 0, 1, 2, 3, 4, and 5 steps. You won't always do this, but it's a good habit to get into when we're learning this technique. Now, the next thing I'm going to do, and this is maybe the first thing that I should have done, but it doesn't matter if we get it a little bit out of order, is that from this point here, I'd like to create a line that's parallel to this line right here. And so I'm just going to use my parallel line construction technique that we learned about in the last tutorial. Basically, it's tilted a little bit, but basically what I want to do is that I want to be able to figure out how to lay my straight edge so that this angle equals this angle, so that the alternate interior angles are equal. So to make that work, I'm just going to copy this angle right here. So this is where I'll take my compass. I will make a mark, the same setting, swing a big arc centered at B, copy the distance between those 2 marks, transfer that distance from where that arc intersects AB to elsewhere on the arc. And then that intersection is where I should draw my line from B2 in order to get a parallel line. So this line is parallel to this line. Now, the reason why, now I'm gonna clean up some of this picture, because now I've got a bunch of stray arcs that are gonna just muddy what's going on. Now that I've got those two parallel lines, this is actually the point in time where it probably would have been smart for me to take my compass, and set it to this arbitrary distance here, and then step off, and then later label, my 5 steps, right? That would have been a good time to do that. Then I'm going to do the same thing from B. My intersection on point B, I'm going to do 1 step, 2, 3, 4, 5. And I want to label those as well, but here's the important thing. This is what helps you keep this straight. I want to label them in reverse order. So instead of starting at B with 0 and going up to 5, I'm going to take this point here and label it 0, then 1, 2, 3, 4, 5, where I end at B. And my goal is that I want these numbers to count in the same left to right direction in the parallel lines. And the reason they are there is that I'm going to connect the zeros to the zeros, the ones to the ones, twos, threes, fours, and fives. And so where those lines intersect my original segment AB, I don't know that that's going to show up. Those blue dots, I'll look for my red chalk later. But where those intersect my line segment AB, that's telling me that this segment is equal to this segment, equal to this segment, equal to this one, and equal to this one. Now why that is not something that's going to be super clear or even provable right now. So we're not even going to try to prove this construction, but it's an important construction, important enough construction that I'm providing it a little bit out of sequence with the rest of Euclid's Elements. This comes out of a later book, and it requires some knowledge of similarity with respect to triangles, and then proportion to really make sense of why this works. But it's a construction that we can use, and it's a fairly precise one. It distributes error nicely, so it's a good way to divide a line segment up into equal pieces like that. And there's nothing wrong with it. I use it a lot. That said, I want to show you 2 more techniques. The next technique is going to be based off of one that you would use in mechanical drawing and drafting, but it actually works for the same reasons that this last technique worked. It's just a little bit hidden that way. What I need to make this work is a ruler that's actually got markings on it. And before filming this video, I forgot to grab one, so I'll probably end up pausing this and editing some of this rambling out and then starting it up again. So. So now we're going to try an alternate approach, or we're going to look at an alternate. So now we're going to look at an alternate approach for taking a given segment and subdividing it into a given number of equal segments. In this case, I'll do 5 equal segments once again. So here's our given segment, and I'm going to draw this one little bit low on the board to make some room for myself. And I want to divide this into this AB into 5 equal segments. Well, to do that, what I'm going to do is from one end of this segment, from B, I'm going to draw a perpendicular line going straight up. And I might need to extend that, I don't know, we'll see. Now, this is where the marked ruler comes in, and this is a big drywall square. But what we want to do is take a marked ruler and line the 0 end up with the A end point. And I want to tilt it until I get a number on this ruler that is a multiple of the number of segments I want to divide this thing into. And so I've got the 0 lined up with point A here, and I've got, you can't see it on the camera, but I've got 35 marked up here intersecting with that vertical line that I drew. And so what I'm going to do, if I can hold this thing steady, I really could use 3 hands here, is, so 1/5 of 35 is 7. So if I take steps of 7 inches at a time along this ruler, and just put a mark, 7, 14, 21, 28, and then 35 is up here at the end. Mark that too, although that's not necessary. So I've got these points. I'll try to highlight them so you can see them. If I were then to go back and take my layout square and slide that layout square along the baseline, trying to see this all at once here, so that this leg is along the baseline AB, and this leg is just touching one of my marks, then I can draw a vertical line till it intersects with my line AB. And I'm going to do that for each of those marks along the diagonal that I made. This is actually a lot easier to do on a piece of paper than it is on a vertical chalkboard surface like this. So you really should try this technique. I think you'll find that it's even faster than that previous construction. And so where these vertical lines dropped onto AB, mark out the points that are the endpoints of each of these 5 equal segments. And so if I wanted to do some other number than 5 segments, maybe I wanted to do 7 segments, in that case I could have still had the 0 mark on my ruler here and the 35 mark on the ruler up there, except that time 1/7 of 35 is 5 inches, and so I would have marched along in 5 even steps. Right, so that's a way to divide a segment into a given number of equal parts. There's one other technique. Let me get this drywall square out of the way. T-square, I don't need it anymore. One other technique that actually can be pretty accurate, pretty reasonable, especially if you're working with a compass that's got sharp points and you're using a piece of paper rather than a dull pointed compass like this. and a chalkboard, but we're still going to demonstrate it here. What you would do is to say, okay, if I want to divide this segment into, in this case, 5 equal pieces, then what I want to do is eyeball the distance, the spacing here on my dividers. Say I think that looks like it's about 1/5 of the distance from here to here. So I'm going to try that. I think this looks about right. And then I'm just going to step it off. So I'm going to go 1, 2, 3, 4, 5. And hopefully you can see that that 5th mark did not make it all the way to the end point. So I had that much line segment left over. And so what I want to try to do is I want to try to open this compass up a little bit, just a little bit more. In fact, I want to open it up about 1/5 of the way of what remains. Again, I'm eyeballing it the best that I can, but that's what I'm going for. Now I'm going to erase my marks. And now I'm going to give you a tip for how to make this a little bit easier on you, especially if you're working with a compass on paper with sharp points. If you are making small adjustments to the distance on your compass, then those marks are probably going to fall in the holes you made in your paper the previous time. And you're going to lose some accuracy that way if you start at the same place you started before. So if you think you're closer this time, we're going to go to the opposite end and then try to step back 1, 2, 3, 4, 5. And hopefully you can see this time my compass, to the resolution that's available on this chalkboard anyway, my compass tip ended up, for all intents and purposes, in this case, ended up on the other end of the line. So I've divided that line up into 5 even steps. So this is an approximation, and it's an iterative approximation, and it's the kind of thing that you're going to do a poor job of it the first few times that you try it. But as you work at this technique, you'll be able, with just maybe 1 or 2 readjustments of your compass, to get close enough for the purposes of drawing a good picture on your paper, like we are here. Where this technique doesn't always work so well is, imagine that you were trying to divide a line up into 29 or 101 or 113 equal segments. Those are going to be very small steps. It's going to be difficult to set your compass to those step sizes. And small adjustments of your compass are going to lead to large errors in the end, once you're stepping towards the end of the line segment, because they compound with each step. So this technique works relatively well for a relatively small number of subdivisions, something like a set of single digits. Now you can milk a little bit more out of it. Suppose you wanted to divide a segment into 15 equal pieces. Well, we've already actually got a good start on that because we've divided this segment into 5 equal pieces. So rather than starting over and trying to squish my compass down to what I believe is close to 1/15 of the distance from here to here, and then step that off, what I'm going to try to do is say, well, now look, if I could divide one of these shorter segments into 3 equal pieces, which actually is going to be hard for me with this compass, but I'll try it. Because 3 times 5 is 15. So I've already divided it into fifths. So if I divide each of those into 3 equal pieces, I will have a total of 15 equal pieces. So I try, I look at this and say, well, there's 1, 2, 3, a little small, so I try to blow it up by 1/3. Now I go 1, 2, 3, and I'm still small, so I'm going to clean up my marks. 1, 2, and that's how I got it. So I've divided this into 3, and then I can just go to each of the segments and divide them up into 3. And that gives me 15. It's a little tedious, but if you don't happen to have a marked ruler, and you don't want to do the first construction, then this is a way that you can get your segment divided up into a large number of pieces. Where this won't even help you is if you've decided that you want to divide a segment into a large prime number of pieces, and then you're gonna have to work with the construction or work with a straight edge, a square, and then a marked ruler. Okay. So those are 3 techniques you can use in different situations to subdivide a line segment into equal pieces. Let's apply it. Let's apply what we know now to developing some constructions for squares and rectangles. Suppose we wanted to construct a square or a rectangle, maybe to be used as a bounding box for a design of a piece of furniture. Well, if we think back to the definitions that Euclid gave us for quadrilateral figures, then squares and rectangles are figures that have parallel sides, opposite sides are parallel to each other, and all of the corner angles are right, they're 90 degrees. So we've got to be able to construct parallel lines and right angles. In a previous tutorial, we looked at 2 ways to construct right angles or perpendicular lines. And we ultimately moved on to just using the layout square because it's the fastest and most convenient way to do it from a design point of view. And that's not, there's no exception to that here as well. We'll continue to use the layout square. But I did mean to bring up one other, and it was a big one other proposition of Euclid's that relates to right angles. And it's actually 2 propositions. It's the very last 2 propositions of book 1 of the Elements. Today we mostly think of them together though as the Pythagorean theorem. And the Pythagorean theorem tells you that if you've got a triangle, and you know the lengths of its 3 sides, then that triangle is right if and only a square of the 2 legs containing what we imagine to be the right angle sum up to give us the square of the remaining leg, or the hypotenuse. And the Pythagorean theorem, we found, has a number of integer solutions to it, the so-called Pythagorean triples. And one of the most common ones, one of the most common triple is the numbers 3, 4, and 5. So if this side is 3 units long, this is 4 units long, then this hypotenuse has to be 5 units long, because we can calculate it. 3 squared is 9, 4 squared is 16, so 9 plus 16 is 25. Well, that equals 5 squared, 25. So knowing those Pythagorean triples, like 3, 4, 5, and there's many others you can look up on the internet if you want to work with other integers. Those are numbers that you can use to construct a right angle if you want as well, because you would just arrange sides of a triangle together, 3, 4, and 5 units long, fit them together, fit those segments together end to end, and you could get a right angle that way. A lot of times, from a design point of view, that's less useful, well, it can be useful for constructing a right angle. But another use of it, so look, you can just mark out, I'm going to do a step of 16, so I've measured from the corner out to 16, because that's 4 steps of 4 inches each. I'm going to measure up this leg 12, because that's 3 steps of 4 inches each. So this is 3 steps to 4 steps. And then if I can measure the distance from this intersection to here, well, I get out to 20. And that's good because 20 inches is 5 steps of 4 inches. So I've checked that this angle is right using the Pythagorean theorem. This is sometimes a theorem that's used in large-scale layout. Like if you are trying to break ground for a building and you want to lay out the corners of the foundation and you want to do it in a way that's going to be square, you can take a bunch of tape measures that are not overly stretchy and measure one of them out to some large multiple of 3, like go out to 30 feet. Take the other one and take it out to the same multiple of 4, so 10 times 4 is 40 feet. And then take a third one and stretch it out to 10 times 5 or 50 feet. So you've got, in steps of 10, sides that are in a 3 to 4 to 5 rational relationship with each other. So you could lay those out, stretch those tape measures out so that they're end to end in a triangle that looks like that, and put a stake in the ground there, there, and there as you're stretching the 3 tape measures together. It takes some helpers and it takes some coordination, but once you've put a stake here, here, and here in the ground, then you've ensured that this angle right here is going to be right. And then you can build the rest of your foundation up off of that good first start. So I meant to include that in the last tutorial and didn't. I think I was rushing to get to lunch. So that's something that we can add to our list of tools for working with right angles. As I said, as we're going to address this problem of drawing or laying out a square, here's what you would do. In the most efficient of possible ways. Say I want to have a square on this baseline. And from this point to this point is the length of the side of the square that I want. My straight edge just moved. So I will take my layout square, put one limb of it on my straight edge, and align the other limb with my left endpoint of this square. And I'm just going to draw a vertical line, and then I'm going to rotate my square and do the same thing at the other endpoint. And so what that guarantees, because my square is true, is that those 2 corner angles are going to be right. Now remember, a square is equilateral and right angled. So what I need to do is copy this length up to here. Oh, maybe the same at this side. Just destroyed my chalk. Okay. Well, at this mark up here, I'm going to lay my layout square so that it is lined up with the edge of that square, and the top edge is available for me to draw along. And if I've been careful, the line from this mark, which I know is right angled, is going to intersect this other side over here at the other mark that I made. And so far, I've guaranteed a few things. This side, and this side, those are equal. This angle, and this angle, they're parallel. But I can do better than that. Or not, they're not parallel, they're all right. Right angle, right angle, right angle, they're all equal. Now, if this is right, this is right. So this side must be parallel to this side because here is an angle that is equal to an opposite so this is an exterior angle that's equal to an opposite interior angle. So those sides are parallel. These sides are parallel as well by the same argument. And this angle and this angle, those have to be alternate interior angles. So that's right. So I've now got all four sides, and this distance I marked out as equal. So all four sides, all four angles are right, and then this side, and this side are equal. I would just need an argument to make that that side is equal. To convince myself fully that I'm dealing with a square, depending on how careful I wanted it to be with that, and then maybe for this demonstration, not that careful is the answer. You can just measure it and see that they're still equal to the baselines that I've started with. If we can lay out a square accurately, then it's not an enormous stretch to lay out a rectangle. In particular, we can now lay out a rectangle where the base is in some chosen rational relationship to its height. For instance, I'm going to do a couple of examples where the base will be 5 steps wide and the height will be 3 steps high. The simplest of those two approaches occurs when you want the rectangle running along some baseline, but you don't particularly care how wide it is in an absolute sense. You just want the width to height ratio to be whatever you choose, in this case 5 to 3. Well, the way you can do that is mark out one endpoint of the base, set your dividers, set your compass to some distance, and step out that distance 5 times. 1, 2, 3, 4, 5. And whatever is left over on either side of those steps isn't going to matter. We'll erase that eventually. Now I'm going to put my compass away and preserve its setting. Then I'm going to take my straight edge and line it up with the baseline again. And essentially follow the steps we took with the square. I'll put one limb of my layout square on my straight edge and align the other limb with the left endpoint of my 5 steps and just draw a vertical up as far as I can. Then I'm going to rotate the square and do the same thing at that other endpoint. Put the square away. Grab my my dividers again. Mark out my 3 steps for the height on both of these perpendicular verticals. And the last step that follow, line my straight edge up with both endpoints. And then connect them. And anything that overshoots these corners, well, that can just be erased. And what I'm left with is a rectangle whose sides exist in a chosen ratio, in this case 5:3. There's my rectangle. If I wanted different proportional or different rational relationships between the sides, I would just have to do a different initial number of steps along the base. And so that's the simplest of the 2 cases where I might want to lay out a rectangle that has sides in a particular rational relationship to each other. Sometimes, though, there's an additional constraint. It might be that there is a line segment that exists somewhere in a design or a geometric figure, and I want to use that entire line segment as the base of a rectangle that has its base and its height in a certain rational relationship. So again, if it was 3 to 5, I wouldn't be allowed to have these leftover pieces of the line segment that I erase after stepping out my 5 steps. I would want to choose my 5 steps so that they fit on that line segment exactly. And we know how to do that. We've got 3 ways to do that, in fact. We could use the parallel line construction for subdividing a segment into a chosen number of equal pieces. We could use the straight edge, layout square, and marked ruler construction for doing the same. Or in a pinch, we could even take our dividers and just iteratively adjust them until they are set correctly to step out 5 steps exactly along your baseline. Whatever way you choose, you've got to divide that entire segment up into your chosen number of pieces. And once you've done it, the rest of this construction proceeds as before. You mark off your steps, you draw your vertical lines with a framing square, you step off that same distance, this step size, however many times you've chosen vertically, and then connect the tops. So it's not much different, it's just that you've got to take a little bit more care on connecting the endpoints of your segment, or dividing up between the endpoints of your segment into a chosen number of pieces. So what we've seen, developing a rectangle into, or drafting a rectangle whose sides exist in a particular rational relationship to each other, is one of the fundamental skills of design. A lot of our designs truly start with a box like this. It's just a bounding box that the overall dimensions of your furniture piece or whatever it is that you're designing fit into. And then you just end up dividing this interior space up into finer and finer pieces until you've got your design. In our next video, we'll begin that process carefully. Our next video will be our first comprehensive design workshop, and in it I will walk through the steps I'd ordinarily take if I was going to design a piece of furniture. In this case, it's going to be a desk with a simple drawer on it. And I don't know if you can hear it in the background, but it sounds like I'm being visited by sandhill cranes today. So it's a nice gift on a cold day inside of a cold shop. We'll see you in the next video.